let's see here. So we go to module 2. So motor architecture. So I want to talk about really 4 things in here. I want to talk about the radial motor, axial flux motor, transverse flux motor, and Halbach array motors, right? All these are essentially the set we consider when we talk about designing a motor. So here is a 2-dimensional view of different motors this is with your outer rotor motor, right? This is not the inner rotor motor. This is essentially a simple illustration when your rotor is outside. So this is a radial flux. This is red is your magnets. Green is your stator. And then you have blue as your windings, right? So this is the outer rotor motor. Axial flux, you basically have the magnets on the side of your cover. And then transverse flux, you have 3-dimensional flux in the windings. So you have set of magnets, set of laminations, and you have splits in them. We'll see more detail in the upcoming slides. And then you have axial flux with Halbach edits, which is where you're able to essentially concentrate your flux. You're able to eliminate all of your leakage flux and concentrate your flux into the air gap and thereby improving the motor performance. So this is the radial flux with the inner rotor example, right? So what you have, the red is your stator and your winding is sky blue color. Then you have magnets, which are essentially your yellow and magenta color. And then you have an axle as blue. So this is your radial flux motor, which is most common today in the world. Okay. Then we have axial flux motor. Now here you see is that your magnets are on a plate, and the green and the yellow are your magnets. This is your winding, and this is your stator core. You can see another view here that you basically have the bindings around these cores, and then your yellow and your green are your magnets, and then this is your back iron. Okay, so that's your axial flux motor. Then you have a transverse flux motor, which can have very interesting magnetic pattern, magnetic path, where you can see the core. Now here you have winding inside the core, and then you have magnets here, right? And you can see the 3-dimensional view of the magnets here. You have magenta, blue, green are the magnets, and then you have this as the core. Now, different architectures give you different magnetic circuits, which can lead to the goal, of course, is can we get more torque? Can we get more efficient speed? Can we get more power from a smaller and smaller volume of space? That's the goal of a motor design, right? Can we eliminate material? Can we eliminate waste so that our motor can be the most efficient part, most efficient component of a drivetrain? All right, so here is another example of transverse flux motor with axial gap. You can see you can get really fancy with magnetic circuits. And here you have a shaft in the middle, and then you have the cores and the winding and then the magnets in between. And then you have, let's see here, I wanted to show you one more part. So here is a Halbach array. So Halbach array is, now it's more complicated to use Halbach array because you are making a single pole with almost 3 or 4 magnets, right? So you basically orient your magnets. You know, you got a magnet pointing to the left-hand side, magnet pointing top, and then magnet pointing right, and then the magnet pointing down, right? So I have to pretty much use 4 magnets to create 1 magnet. But the beauty of this is that I can position my flux in such a way that it is going all of it to the air gap. And as a result, I have an opportunity to actually eliminate some material. So I don't need a back iron, right? That's the beauty of why do you need normally a back iron is because you're trying to provide a return path to the flux. But if your flux doesn't go to the back, there is no flux here. You can see the flux is 0 here, and the magnets essentially focus the arrangement of these magnets helps us focus everything to the air gap. Now you have this beautiful magnetic structure which you can leverage to have a motor which has less material. Okay, but they are a little complicated to make simply because you need different arrangements of the orientation of the magnet. All right, so let's go back to the things I needed to cover here. Okay, so all right, so if you look at the radial flux, it's one of the simplest magnetic structures, right? It's 2D magnetic structures, easy to analyze. There are analytical equations you can use, and it is pretty simple to be able to come up with a radial flux design. Okay, now axial flux is a 3D magnetic structure. So without any transformation, you cannot really use a 2D FEA program to do it. Analytical solutions are limited in axial flux design. And lamination manufacturing is tricky. AFMs can outperform RFMs under a set of narrow conditions. Number of poles must be high, axial length must be short, right? So those are some of the advantages under which, or some of the parameters under which axial flux motors can shine, okay? And transverse flux is also a 3D magnetic structure. And there are not a lot of people who have used transverse flux. There are a few who have been commercialized. I think there's always a debate how effective transverse flux motors are. They are perfect for soft magnetic composite application. You can actually mold the poles the way you want. And that's the beauty of it, right? So, okay, can you really exploit this ability to make a pole? Again, the goal is how can we maximize the flux in the air gap without saturating our materials? If you can do that, then you can exploit the interaction between the current and the magnetic field more effectively. Okay, so we talked about the Halbach arrays, and here is a motor which you can see, one of the high-speed motors, which was made, I think, few thousand RPMs, where you have magnets here, you have a lit wire, because you can have a pretty substantial proximity effects in the winding, so your currents can go pretty high. So you have to use lit wire, and you have a carbon fiber backing. So you can get a pretty good power from a very clever design using Halbach arrays. Okay, so here is a table of various motor architectures. Before we delve into the table, are there any questions I can answer? Okay, all right, so let's look at, I'm going to go through, so we have got architecture, flux direction, key feature, application focus, pros and cons. So radial flux motor, flux direction is radial. Key feature is common, mature design. General industry, EVs, fans, mature. Pros is mature, good performance, easier to manufacture. Cons, limited cooling, longer motor for higher torque. All right. Axial flux motor is compact, high torque density. Application focus, e-bikes, aerospace, EVs. Pros, high torque density, better cooling, compact. Cons, manufacturing complexity, tight tolerances. Transverse flux motor is essentially, so you have a transverse flux direction. So it goes radially and axially, essentially. That's what it means. High torque, modular, direct drive, robotics, very high torque density, direct drive suitability, complex design, higher losses. It is also called the flux switching PM motor. Now, the flux switching PM motor, essentially you embed your magnets in the stator winding, so in the stator core, and it can have interesting magnetic circuits to wrestle with. So the flux direction is radial. You have key feature is robust rotor, stator magnets. Application focus EVs, high reliability systems. Pros, high reliability, robust rotor. And the cons is high core losses, complex flux paths, right? And then there is the hybrid excitation PM motor, which is a wound field, PM plus wound field. And then you have a linear permanent magnet motor, which is essentially linear, all right? So So before we go to the next part, we are at a time where we need to take a break. Any questions so far?
Sir, what is typical flux, like what is the flux direction in typical BLDC motor? Like that
Sorry,
is
could you
used.
repeat that again, Simran? What is what?
What is the flux direction in typical BLDC motor?
So
I mean, yeah.
yeah, so flux direction. All right, so let's look at the flux direction. It's going to be in a typical BLDC motor, you're talking about a radial flux direction. Most of 99% of the motors today use radial flux motors. Of course, recent years, there are more, axial flux motors being used, but still their prevalence is still very, very small. And in the radial flux, you have a lot of flavors we'll talk about, but most of the motors have radial flux direction. So that means the direction is from it's basically going from the center of the motor to the outer diameter, right, in the straight line.
Okay. Okay, thank you.
Yeah, you're welcome. All right, we'll take a 15 minutes break at this point of time. Hopefully everybody's still awake, and we will be back in 15 minutes. Thank you so much. All right, so let's get started again. Any questions before we start? Can everybody still hear me and see me and see the screen?
Yes.
Yes, sir.
Very well.
Yes.
Okay, wonderful. So welcome back. Hopefully everybody got a bathroom break or a coffee or something of that sort. Let's see here. All right, so let's talk about current state of the art. What is our technology today? So if I look at, it should say propulsion motor plus inverter technology. So when I look at the technology, I can look at inverted or non-inverted technology. I can look at magnet arrangements, pole configurations, number of phases, materials, winding methods, control methods, inverter architectures. Now we have various flavors of inverter architectures, which we won't go deeply into, but we will talk about power state design in the later part of the workshop. In terms of control methods, we have trapezoidal, sinusoidal, field-oriented, space vector, sensorless, fuzzy logic, etc. And winding methods, we have distributed or concentrated windings. And again, you can have also in terms of axial flux motor, printed windings. Materials, we have choices of soft magnetic composites, laminations, neodymium, iron boron, samarium, cobalt, etc. All right, so this is the world we have. And all right, so this is essentially what we deal with in terms of our areas we control, designing a motor and inverter system. And so here are various motor architectures, the two-level voltage source inverters, and we'll talk about that briefly in the next slide. Three-level neutral point clamped inverters, multi-level inverters, matrix inverters, current source inverters, Z source or quasi Z source inverters, dual inverters, multi-phase inverters, right? So in terms of, so this is a two-level inverter. So two-level inverter, essentially you can see these pulses here, which are not really very clear, but they really toss between, flip-flop between plus VDC by 2 and minus VDC by 2. So this is basically a two-level inverter. You have got three legs, three bridges, three half bridges, and then you have, this is your midpoint. So you basically are switching between plus VDC by 2 to minus VDC by 2. If you look at the harmonic contents here, you have harmonic contents. You, of course, have the fundamental, and then you have this first spectrum of harmonics at the switching frequency, and then you have 2-time switching frequency. Okay, so you do have higher EMI issues here, it's simply because these will degenerate itself into megahertz frequencies, which can cause issues with EMI, RFI, etc. Now, you have a three-level neutral point clamped inverters where now you're going not only plus VDC, you're also going 0 and negative VDC. So you basically have plus VDC 0, 0, negative VDC, etc. Now, this has the complexity. You still have 3 bridges, but you have now increased your MOSFET quantities to 12, and then you have additional complexity of driving these MOSFETs. However, you do have the benefit of shifting your frequency spectrum from the first switching, fundamental of the switching, to the second, 2 times of the switching frequency, okay? So some alleviation of your EMI RFI issues. And then this is another 3-level neutral point clamped VFD, or the inverter. We call it an I-type inverter, where now you have got, again, more switches. So you're still doubling your number of switches, plus you're adding your diodes, okay? So very specialized inverters. And then let me briefly talk about current source inverters. Let's see here, what do I have next? Okay, so let me just briefly touch about what a current source inverter is. So essentially, current source inverter is where you are trying to provide current, controlled current to the load. So you put an inductor here. And in terms of these source inverters, you replace this inductor with a combination of resistors, capacitors, diodes, where you can have the inverter double, a double duty, do a double duty, work as a buck boost converter as well as an inverter, right? So those are some of the other inverter architectures which are in the market, in the industry, okay? And so let me go back. So these Z-source and quasi-Z-source is a variation of the current source inverter. Dual inverter is where I can have 2 inverters run 1 motor. Essentially, when the motor is a high power motor, and I want to be able to, in order to deliver the high power motor, it makes a lot more sense to use 2 inverters. So you split the winding. In the case of induction motors, you can actually run 2 inverters in parallel. In case of permanent magnet motors, you essentially have to phase shift the winding. So you have a 6-phase motor, and then you can run with 2 inverters at the same time, right? So that's a dual inverter. And then you can have a multi-phase inverter. We'll talk about, using inverters for more than 3 number of phases, okay? So any questions so far? All right, so let me briefly talk about, I have had a privilege to work on 5-phase motors, 7-phase motors, 6-phase motors, etc. So is there an advantage of using a 5-phase motor or a 7-phase motor? What are your thoughts in terms of using more than 3 phases? Any wild guesses? Anybody?
Maybe we are using more than 3-phase motors in order to reduce our external filter. So if you don't want to run a motor, you want a resistive load that you want to filter, and you want a clean sine wave, you are using more than 3 phases.
Right. Yeah. So that's one advantage of having a number of phases, higher number of phases, is you can essentially have better filtering. You can have cleaner waveforms being delivered to your motor. You can also now when you're using a 3-phase motor, you have a higher current per phase. When you have a 5-phase motor, you're going to have a less current per phase, so you can distribute the current into more devices without compromising your power architecture. So the number of the filter capacitor quantity goes down. So when you have a bus voltage capacitor, that goes down, and your controller complexity does increase with the 5-phase and 7-phase, because today you have microcontrollers or DSPs that can give you 10 PWM. So you can have you can have a complementary PWM. So if you have a 5-phase motor, you need 10 PWMs, right? If you have a 7-phase motor, you need a 14 PWMs. So you need a pretty high power DSP processor to be able to do that. So So it does include, it does increase your controller complexity quite a bit. But if you have a very specific application, you can think about using 5 and 7 phase motors, etc. So, and now let's talk about the winding methods. Now, my favorite winding method is called fractional slot concentrated winding. And why it is my favorite method is because it gives us high power density, high efficiency, short end turns. We don't have a lot of leakage flux because of the way the windings are done. High slot fill factor. We can get up to 40% with the traditional winding methods. Low cogging torque. You can design the motor to have a very low cogging torque. You can have remarkable flux weakening capability, and you can have a pretty good fault tolerance on these in these architectures. So, and now let's talk about the motor optimization. When we look at the motor optimization, you're going to look at number of stator slots, number of magnets, and then there's a term we use called number of slots per pole per phase. We look at the rotor outside radius, stator outside radius, radius ratio, which is the rotor over stator, motor constant, Newton meter per square root of watt, skew factor, and cogging factor. So I'm going to give you a few examples for you to have a feel of how these parameters interplay into optimizing a motor design, just to get an idea on what a good motor looks like. All right. So here is a table where we have got the number of stator poles, number of motor poles. Then you have the stator per pole per phase. Then you have the ratio. Then you have the torque constant, the skew factor, and the cogging. Okay. Now, in this experiment, we basically said, okay, we're going to vary the number of, we basically are trying to reduce this. What happens if we were to reduce number of stator poles per phase? Okay. Now, as you see that when this number goes down to 0.3, okay, and we have kept this, the physical dimensions, the ratio between the rotor and stator is the same. Okay. Rotor, this is inside rotor motors. This is not outside rotor, inside rotor motors. So this is kept constant. You see the torque could be increased from 0.82 to 1.28, right? So that's a massive increase in torque. And also you have a pretty good reduction in cogging torque, and cogging, I guess, remains about the same. Okay, or the skew factor remains about the same. So what does that tell you? So here we can see you have, I mean, you can, of course, derive other conclusions from this table as well. But this factor here, stator per pole per phase, seems to be a critical factor in this case, where if we can reduce it, we seems to be hitting a home run. Okay, now let's go to, here's another example where we have again tried to reduce the stator pole per phase and gone from 36 to 12, and it resulted from a torque improvement of 1.12 to 1.39, right? And then here's another example where we went from 27 to 18, and you can see this is going down to 0.3, and we have had a 50% increase in torque here, okay? Now, mind you that this is inner rotor motors, and this you have to take this study with a pinch of salt, because you are increasing your, when you reduce your number of stator slots, you essentially are improving your ability to push torque, copper in the slots, right? That's the part which is, there is, the more copper I can have in the slots, I have a better efficiency and better torque production. If I can increase the number of turns without saturating the material, then I can, and also improve the efficiency, resistance of the motor, then I can have a better torque, right? So this is basically, that's what it's telling us, is by having this ratio go down, you're able to optimize your torque production, because you're able to have more number of turns without compromising your ability to have without compromising the efficiency. And so here is essentially your Km being plotted as versus keeping, a ratio of rotor over stator. Obviously, when you increase your rotor, automatically your torque goes up, right? But if you optimize, so the bigger the radius you have, the more torque you produce, right? So this is a linear relationship, which is a no-brainer for us to follow. Now, and here is your torque versus stator poles per pair. And you can see here a stator pole per phase. I'm sorry. So you can see here that your maximum torque occurs at lower NSPP value. Okay. Any questions on this one? So when you're looking at the motor performance, you can see that there is I call it small tweaks, but they may not be small tweaks in your eyes, can make a big difference in motor performance, right? You have to know, okay, with the given, you have, when you take a certain geometric dimension you work with, it automatically imposes certain rules, certain restrictions to exploit that, right? Can you exploit that to get maximum torque, maximum power out of that geometry? Of course, then there's also a limitation of a speed. I can reduce the size of a motor if I can spin at very high speed. Okay, I can always do that by having you can say a gearing mechanism in place. I can also increase my torque, right? So it's important to realize that once your dimension is set, then it imposes a lot of restrictions, and your ability to exploit those restrictions is the magic in the motor design. And it requires significant optimization effort to be able to get to the right motor design. Okay, and what my advice always has been is one must engage a well thought out design of experiments, look at all the facts and say, okay, are you able to get the maximum flux density under all operating conditions in the air gap without saturating your materials so that you can get maximum torque and maximum power out of the motor. Okay, so we're going to go to magnetic architectures. Are there any questions at this point of time I can answer? All right, so let's look at some of the magnetic architectures we have discovered over time. So in terms of rotor architectures and stator architectures, obviously we can divide them into, and these are all more or less radial flux architectures we're going to talk about because that's most prevalent topology we deal with. So interior and exterior rotor and stator architectures, that's what we're going to look at. Okay, so starting with rotor architectures, interior surface mount magnets. And here we have several different flavors: radial magnets, 2 radial magnets per pole, 3 radial magnets per pole, 4 radial magnets per pole, or parallel magnets. Okay, and so let's look at the surface mounted with radial magnet. So this is your rotor, and you have got 4 magnets here. So this is one very basic architecture. The issue with this architecture is that high speeds, these magnets, because of centrifugal forces, can fly apart, and consequently you can have damage in the motor. So here is essentially a bread loaf magnet. These are also surface mount magnets, but you have gaps in between the magnets. Same issue as now. Obviously, one of the things we want to do is minimize the amount of magnets we use in the motor because magnets continue to be expensive, and there continue to be more and more issues of sourcing magnets from China. So if we can reduce the use of magnets, it's very, very important, very beneficial to the motor design. So can you reduce your magnet usage in the motor? So you can start looking at surface mount magnets where you have more of a parallel structure, but you have less utilization, less use of magnet material. Here is your surface mount with 4 radial magnets per pole. Again, when you go to higher speeds, you're also trying to cut down on losses in the magnet. So you can start dividing the magnets up so that you can reduce the eddy current losses in the magnets. So that's another consideration you have to have especially at higher speeds, and you're looking at a surface mount design, you have to have dissection of the magnets so that you can reduce your losses. Here is, you have, now this here, you could design it cleverly so that the magnets don't fly out. So you can inset the radial magnets inside the rotor. Spoke magnets, we will talk about embedded magnets and non-embedded magnets. So here is your spoke magnets. Now the beauty of this is the magnets are very secure inside the rotor, right? Now, why would you want to use spoke magnets? Any guesses? Any wild guesses?
Because we can go higher speeds.
Correct. That's correct. We can go at higher speeds. And also, one of the things we will discover down the road is when you start using these embedded magnets, your magnetic circuits become a little more interesting. You have now different flux lines, different flux linkage between your direct axis and Q axis, and you can have additional torque component which is available to you. So we'll discuss that in the upcoming slides. All right, so here is spoke with non-embedded magnets. You can slide it from the circumference of the rotor. Then let's talk about the bread loaf magnets. Here you can see how these are. Again, different variations based on manufacturability, based on speed considerations, based on usage of magnets, right? So you can have all these very interesting structures. And here's the IPM with lateral magnets. Again, you can see now, when we begin to go into these kind of structures, again, we are trying to really shape the flux in the air gap, right? The game happens in the air gap. So if you can have a beautiful flux density in the air gap, then you win the game, right? The problem is that the air gap is also the place where a lot of disturbance happens, because the air gap is going over a lot of discontinuities when you have stator poles. So those discontinuities create harmonics. Those discontinuities create noise, right? So we have all these methodologies where we can say, can I shape the flux in the air gap so that I can have this noise-free, harmonics-free torque production, right? So some of these architectures are aimed at achieving that particular goal. So you can see how all of this is an attempt to shape the flux density in the air gap. Here's the wound square type. And let's see the rotor architectures. Let's see here. So this is outer rotor exterior. I think it's pretty much similar lines. So this is your stator architectures. Now, stator architectures, essentially here the game is, can I stuff more copper in the stator? The more copper I can stuff, the better performance I can get, the more number of turns I can have. So there's a game optimization between the stator material and the copper material. So here's again, you can see with the different shapes, you're trying to optimize the use of your copper. Square with curved tanks, parallel tooth, you're trying to improve your manufacturability. Here, you're trying to, this is great for distributed windings, general round, which has been traditionally used in induction motors. Parallel, you could, again, if you have concentrated winding, you're trying to improve your manufacturability with this kind of design where you can just stuff your coils inside the stator. Here you have really no teeth at all. Okay, interior stator architectures. Let's go through them real quick. You can see here on similar lines how the copper is being arranged inside your stator. Square with cylindrical tanks, round, parallel, slotless, and that's it, right? So you can kind of get a flavor of all the different things you can do. It boils down to, if I look at the most useful architectures, I would say it would be the IPM designs and the surface mount magnet designs, right? Those are the two flavors essentially we play with in terms of getting surface mount magnet design is simpler to use, and IPM design is they want to exploit perhaps more torque density, etc., in being able to have a smaller motor design. But it does have a complexity in controls we'll discuss in here in the upcoming slides. Okay, any questions before we go to module number 3?